this one. Okay, yes. I've got to share my screen. Okay, can you all see from online? Just let me know.
Yes.
Okay, thank you. So let us start our second lesson, which is going to be on the subject I listed here. We will start with describing what happens when some waves interact with interfaces, and the wave will be able to reflect and transmit through it. Then we will describe what are guided waves that propagate in plates, and also present the semi-analytical methods for the determination of the dispersion curves in waveguides and also in periodic systems. Then I'm not sure I'm going to do that all. Also, I mean, I'm not sure I'll be able to discuss also the fourth point, because this is a lot of material, but if we won't be able today, we will do that on Friday, which is the forced response of the waveguide, which will be obtained by making use of the principle of reciprocity. Then let us start. The references are basically the same, even though this slide is old, so there is something missing. The one I reported and the first presentation is there is one extra reference. And so we will start with normal incidence. Normal incidence is what happens when a wave with a plane wavefront encounters a plane surface where there is a change in the material properties You've got to imagine a plane wavefront, which is represented by this black arrow, and analytically is represented by this displacement field, which are all parallel. Imagine a P wave with amplitude I, which is generally assumed to be a unit, and they propagate along the x direction. The material on the left, the blue one, has a given wave propagation velocity, which is c sub L1, and the pink material, which is the one on the right, has a different wave propagation velocity, which is c sub L2. Then it happens that a part of the incident wave is reflected, and this is represented by this red arrow. You see that this one is a wave propagating from left to right, and this red arrow is some other wave propagating from right to left. You see that it is represented in the exponential. And a part of the wave is instead transmitted to the pink material, and the wave is represented by this blue arrow and this equation, which is again a wave which propagates from the left to the right. The different amplitudes are represented by this capital R and capital T and capital I for the incident wave. The amount of reflected and transmitted energy can be determined by enforcing the boundary conditions, which are the conditions that have to be satisfied on this surface. And these are basically continuity of displacements and equilibrium of forces. Okay, if we've got a P wave with a plane wavefront, the only displacement component different from zero is the horizontal component in this case, which I have called U. And this is parallel to the direction of propagation. And the only stress component is this, different from zero, is this normal component I have called sigma sub xx, which is tied to the displacement component by this relationship. You see that if u has this expression here, when you derive by x, here you find a quantity which is exactly equal to the displacement u, but it has got different phase because this is multiplied by the imaginary unit, which basically rotate the vector by pi half, and it is proportional to u, and it is basically multiplied by the wave number. If we enforced continuity of displacement and equilibrium of forces, we obtain two equations which are made like that, because you see that all the quantities are represented by this term, these exponential terms, which describes propagation in time and space, which is exactly the same for all the terms. Therefore, we obtain these two algebraic equations that can be solved and enable to obtain the ratio between the reflected amplitude and the incident amplitude, and by the transmitted amplitude and the incident amplitude. So you see that from these two equations, the amount of reflection and transmission depend on the ratio between these quantities, which are the product of density and wave propagation velocity. This product, it is called acoustic impedance, and it depends on the material properties. So all these quantities, as you see, can be expressed as a function of the ratio of the acoustic incidences of the pink and of the blue material, so that we can derive expressions like that. And if we represent the transmitted amplitude and the reflected amplitude as a function of the acoustic impedance, which is what is done in this diagram, you see that the amount of transmission and the amount of reflection change as a function of the ratio between the impedances. It is interesting to observe that ρ equal to 1 means that the two materials have the same properties. So when the two materials have the same properties, basically the interface does not exist. And in fact, the result we obtained is correct because there is basically no reflection. R equal to 1 means no reflection. And the wave is totally transmitted. In fact, you see that T is actually equal to 1. When we have values of this ratio which are smaller than 1, this means that the first material, this means that this is large with respect to that. So the first material is much stiffer, which means that the propagation velocity is larger, or heavier than the second. And in that case, there is a ratio between transmission and reflection, which is determined by these ratios. Actually, you have to observe that also values of R larger than 1 are possible. And in fact, when R is very large, it means that the second material is very stiffer and or heavier than the first one. And in the limit, the whole wave is reflected and there is no transmission. You have seen something here in this diagram that might look like a mistake. you see here for R nearly equal to 0, you see that T is equal to 2. What does that mean? In fact, this is not a mistake, because if you check out the work done by the internal forces per unit time and unit area, you obtain a relationship which is this one. Therefore, independently of R, you always obtain 1. So energy is actually conserved. What happens is instead that at the interface between two materials whose first layer is much stiffer or heavier than the second, there are concentration of stress. And this is in fact one of the typical causes of the bonding between layers, which present properties that are very different from one another. The procedure that I have described can be implemented for waves encountering double or even multiple changes of material properties. You've got to consider that this drawing can be representative of a multi-layer material. And in this case, the difference is that you've got to account for what happens at every interface. And in this case, the number of amplitude that are unknown is much greater. But it is true that the number of unknown is greater, but also the number of equations is greater. Therefore, you've got to enforce continuity and equilibrium at each interface. And in this way, you are able to determine all the amplitude of the reflected and transmitted waves. I am showing here to you some experimental results that describe what can be observed experimentally when you have changes of material properties. In this specific case, the change of material properties is given by a change of cross-section. We realized this experiment with this bar. You see, it is represented here. It is a bar which is excited on the left end by a hammer, which gives a forcing function like that, and generate a wave which is observed at this point, which is called CH1. It generates a time history of a disturbance, which is exactly this one. This is the incident wave. This is what we called I in the previous expression. Here, at this point, sorry. We have a first change in the cross-section, then a stretch of bar with constant cross-section, and then a second change of cross-section. In this case, the impedance, since the weight of the material is exactly the same, because this reduction in the area was machined. Some material was removed from. Sorry, I see someone. Okay, sorry. Some material is removed from the bar, and the change of impedance is just given by the square root of the ratio of the areas, where A2 is the area of the cross-section in the reduced part, and A1 is the area of the cross-section in the uniform part. So you see here what happens when you observe the time history at channel 1 and what happens at channel 2. Channel 1 is placed before the discontinuity, and channel 2 is placed after the discontinuity. You see here, this is the wave reflected by the first change in cross-section. And this other one is the wave reflected by the second change in cross-section. And here you see the wave which is transmitted. Now, I should say something here that I've not precisely said before, because before we saw that exponential solution in time and space can solve the equation of motion. But actually also the equation of motion for bars, for instance, also accepts a solution which is called the D'Alembert solution, which is a solution that is made like that. Just let me open lesson 1, which is here. Okay, here you see that whatever f or g function, which is a which can be expressed as a function of the quantity kx minus omega t, can be a solution for the equation of motion. So if this is this f, this holds. This D'Alembert solution holds also, since everything is linear, for superposition of solutions. Therefore, this consideration not only holds for harmonic waves, but also for other shapes of the solution. Therefore, this amplitude concerns also this other reflected and transmitted wave. You see, after all, that the transmitted wave has exactly the same shape as the incident wave. The only difference is that the amplitude is different, and the ratio between this and that is nothing, between that and that is nothing but t. The ratio between this one and that one is nothing but r, exactly what we have here. Obviously, here we have another wave, which is reflected by the second change, which crosses twice. And for this wave, the incident wave is no longer that one, but that one. So this is basically the transmitted part of the first reflected wave. It is a series of reflection you can calculate like that, using this different contribution. And the interesting thing is that when the characteristic of the discontinuity change, this enables also to make consideration on the response, or inversely, to pick up information on the characteristic of defects of the defect based on the reflected and transmitted wave. Just check out these two time histories. You see that here the two waves can be distinguished very clearly. You see, the first one is just reflected by the first change in cross-section, and the second one is the wave reflected by the second change in cross-section and then transmitted to the first part of the bar. But when the changes of cross-section are narrower, these two waves superimpose. So you see that here, for instance, Here, A, which is the length between the two changes of cross-section, is shorter. So they start superimposing. And in the limit, if A is very, very short, you cannot see, because you can't see the discontinuity, because the two waves completely superimpose. What does that mean? It means that the smaller the disturbance you want to, the smaller the defect, or the smaller the object you want to observe, the smaller wavelength you've got to use. The idea is that to observe something, you've got to use a wave which has a wavelength which is the same size as the characteristic size of the defect. Otherwise, superposition, you won't see anything. And this is true for whatever phenomenon, even for light. If you want to see things that are really, really small, you've got to use very small wavelengths. Now, up to now, we've seen what happens when the incidence, the wavefront, is parallel to the change in to the surface, where the change of properties occurs. But what happens if we have oblique incidence? When we have oblique incidence, we have a phenomenon which is called refraction. So imagine that we have two different materials, pink and blue, and we have a wavefront which is inclined with respect to the surface where the change of material properties occurs. It happens something that can be studied either geometrically or analytically. Basically, the results are the same, but I like this explanation, which is a geometric explanation, and enables us to derive what is called the Snell's law. The Snell's law enables to express the angle that the normal to the wavefront in the second material, this angle, forms with a line which is orthogonal to the surface where the property change as a function of the speed velocity in the two materials. And it is very easy to determine geometrically. Look, just pick up the segment A1 and assume that this segment is part of the wavefront. Now, according to Huygens, you can imagine that circular wavefront emanate from each of the points of this wavefront. The fact is that if you pick up two equal time instants, if the velocity of wave propagation is different, in the same time, the wave travels different distances. Then, in the material 2, the distance traveled will be, let's say, AD, while in the material 1, the distance will be BC. Okay? And the length AB and DC is assumed to remain constant. Then, with a few geometrical relationship between this triangle, you can derive picking up obviously the same time, this relationship between angles and wave velocity. You see that time is the same. So in this case, in this specific drawing, I have assumed that the speed in the second material is larger than the speed in the first material, because in the first one, in the same time, a longer segment is in the same time, no, sorry, it's the opposite. in the first material, a longer segment is traveled in the same time. Therefore, in material one, the velocity is larger. And this is exactly what happens.
Isn't it the opposite? Because it took longer distance means the speed is less. Right?
No, same time. Same time. Same time. Okay, and this is exactly what happens if the two material properties are different. You see, you've got a wavefront which encounters this change in material properties, and then the angle that the normal forms with the wavefront is changed. And in particular, this is a case where C2 is smaller than C1, like in that other case. So the wave in the second material is compressed. And yes, the wave is compressed. Frequency, yes. Frequency is frequency. Frequency is not affected. What changes is the wave number. In fact, if you observe this relationship, lambda, which is the wavelength, which is the opposite of the wave number, is equal to C omega, to the ratio between the speed and the frequency. So if C decreases, also lambda decreases. So smaller wavelength means narrower crests, like in this animation. An important aspect in the case of refraction is the critical angle. So you see, this is exactly what happens. You've got an incident wave and a refracted wave. This is done for a ray of light. This example I picked it up from Wikipedia, but it's perfectly equal in the case of waves in solid. You've got a ray and a reflected ray. If you change the incidence of the ray incidence, also theta2 changes. Therefore, there is some angle when the transmitted wave is addressed in the surface. And this is called critical angles. For incidence angles larger than the critical angle, like that, the wave, the incident wave, is totally reflected. So the wave cannot propagate in the second material. This example in this drawing is made for light, but for materials that are used in structures, for instance, isotropic, solid isotropic and homogeneous material as those which we saw this morning, we've got two waves, P waves and shear waves. Therefore, you've got two critical angles. The first one, which depends on the relationship between properties of the two materials, is, for instance, an angle which blocks some kinds of waves, let's say P waves. Okay, so in the second continuum, only shear waves can propagate. P waves are all reflected into the first material. But in this case, you are going to have a second critical angle. So if the incidence angle increases more than that, not even shear waves will be able to propagate in the second material, but all the waves will be reflected into the first material. And this is, mode conversion. You've probably heard of mode conversion, and this is due, I actually should complete a little bit this section because I would like to show it better. And mode conversion is what happens, again, when there are these changes in material properties, and it happens that some kinds of waves, let's say P waves, can be in the second material partially converted to shear waves because of the continuity of displacements to be satisfied on the boundary. So oblique mode conversion happens together with refraction. So if you've got a continuum, you will see either refraction and mode conversion. Now, let's move on to one of the other subjects that are related to reflection and transmission, which is guided waves in plates. Here we will consider only plates that are traction-free. That is, it is a layer of material that have free stress conditions on the upper and lower surfaces. Although the procedure we will introduce are very similar to the one we used in when we were studying bulk waves, and are used in a countless numbers of guided waves problem. That may also include pipes, multi-layer plates, and so on. Basically, the basic difference between bulk waves and guided waves is that bulk waves travel in the bulk of material, totally away from boundaries, while guided waves arise in a medium which has boundaries that enforce a specific propagation regime in between the boundaries. And in this case, the solution is represented by a function which is the product of a traveling part and of a stationary part. And the stationary part is called wave mode shape. So, as I told you this morning, we have a regime which is something in between structural modes and wave propagation. Again, bulk waves and guided waves are governed by the same, exactly the same field equation. But for guided waves, you've got to add the boundary conditions. So you can imagine that in this case, in the case of guided waves, you no longer have just one eigenvalue problem. You have got a sequence of eigenvalue problem, which explains all those lines you saw this morning. So you've got two eigenvalue problems you've got to solve in a sequence. And I'll show you how this happens in place. So let us start from the case of bulk waves in the case of a homogeneous and isotropic plane. Equations, you know them, we saw them this morning. They are these ones. But now these equations have to be satisfied together with some boundary conditions on the free stress on the upper and lower surfaces. This means that this product, where sigma is the stress, has to be 0 when h sub 3 equals plus h and when h sub 3 equals minus h. How can we proceed to solve this problem? There are mainly two methods. One is called the method of Helmholtz potentials, and the second one is the partial wave technique. The method of Helmholtz potential is very elegant, but its application is limited to isotropic plates. If you want to do something more general, we've got to use the partial wave technique. The partial wave technique is very useful and enables also to solve more complex cases, like composite material plates, or can be even applied to new and different materials and cases. The technique works like that. Similar to what we did in the case of the three-dimensional material, you remember that we had a wave number which was a vector. Because it was just k, the modulus, times n, which is the normal to the wave front. What do we do now? We say, okay, we assume that the wave has to propagate along x1. Therefore, we assume a solution which has this form. We've got an amplitude, which is a displacement field that varies along the stiffness of the plate, plus a propagating part where the propagation occurs only in the plane x1, x3, which is a plane orthogonal to the plane of the plate. This is the plate. So the plane of the plate is x1, x2. The, let's say, cross-section of the plate is along x sub 3. So u function of x sub 3 is the wave mode, and this is the propagating part in the plane x sub 1, x sub 3. Then, if we pick up this solution with this trick of expressing everything as a function of just one wave number, so we pick up this ratio between the two wave number and substitute this tentative solution in the field equation, we obtain a first eigenvalue problem, which is this one. That's not enough. we not only obtain a first eigenvalue problem, but we also observe that the equation of motion decouple. You see that you've got this one, the second one, which implies displacements according to U3. Who is U3? Is the direction which is orthogonal to the plane where propagation occurs. Which kind of wave is that? It's a shear wave. This is a shear wave, while the other two waves imply displacement according to x1, p-like waves, and according to u3, bending waves. So, if we solve this eigenvalue problem, this can be done analytically, we come up with 6 roots. 2 roots are tied to the shear wave problem. And another 2 roots, because you see that here you've got a squared, okay, take the roots. The other 2 roots are tied to the other waves that are called Lamb waves, Rayleigh-Lamb waves. But that's not the end, because that one was just the first eigenvalue problem, the one which was deriving by the bulk equations. Now we've got to satisfy the boundary equations. Then we express our solution as a function of the solution of the first eigenvalue problem, and then substitute everything in the bulk equation and get, again, 2 separate eigenvalue problems. One is for shear waves, and the second is for Lamb waves. Now, the problem for shear waves, lovely. It's got an analytical solution. It's this one. You see? Wave numbers as a function of alpha. The second one for Lamb waves is alpha is known analytically, so no problem for alpha, you know it. Second one, not so nice. It needs a numerical solution, but it's feasible, okay? It's this expression one. It's not like crazy. This means, all this result means that the roots K1 have to be found in a given explored range that can be a range of speeds or a range of frequencies. Then the values entered in the first eigenvalue problem, and then the second one has to be solved. Just wanted to show you something. Yes, we will go back. If you do all these operations, okay, you obtain results that are something like that. These results concern an aluminum, aluminum steel. No, this is an aluminum plate. An aluminum plate. And you see that I have represented them using different diagrams. They are often all called dispersion curves in the literature. The first one is omega as a function of k. You remember the case, the one-dimensional case? It had only one of these curves, just this one. This one has more than one. And you see all these points, they are all cutoff frequencies. All cutoff frequencies. Each one of these modes that has these phase velocities and these group velocity has a shape, and the shapes are the distribution of displacements according to x2 that are reported in these diagrams. You see, 0 means SH0 mode, that is the first shear mode. What is that? It's a wave mode where all the points move of the same quantity. It is exactly this one. You see, all the points move of the same quantity. Displacement is orthogonal to the direction of propagation. This is an SH0 mode. The other modes are more complicated. There are nodes, and they become more and more complicated as you go higher with frequency. For instance, the first mode has a shape, which is this one. Second one, 2 nodes. Third one, 3 nodes, exactly like the modes in a free beam. This is very similar to what happens to the shapes, to the mode shapes. But these are wave modes. They are not modes. They are shapes that propagate in time and space. What is interesting for the shear waves is that each one of these curves corresponds to a shape that remains the same with frequency. Meaning that the shape corresponding to this motion for SH1, this is the way this is called, is exactly the same as the shape for the motion here. And that is the same for all the shear waves, shear wave modes. But unfortunately, this is not the case for lump waves. The solution for lump waves is something like that. You see, I have reported here some diagrams that are pretty much the same as I did before for the shear waves. You have a dispersion curve where you've got wave number as a function of frequency. Actually, this is the product between thickness and frequency. Phase velocity as a function of this product, group velocity as a function of this product. You see how complicated is the propagation in this plate. And you see here that there are many different modes, and they all have names. You see that it's not me, but I just reported something which is typical in the literature. They are called A0, A1, A2, and so on. S0, S1, S2, and so on. S stands for symmetric mode. A stands for anti-symmetric modes. And what is the shape of these modes? Well, first of all, we've got to say that the shape of these modes, differently from what happens with the shear waves, changes with frequency. And here, I've reported the shape of the same mode at 2 different frequencies. This is the symmetric mode. You see what it's like. A symmetric mode that propagates along x1 has displacement according x1, which look like a pressure wave. They are symmetric with respect to the plane of the plate. But this is not all. You see that it's got also displacement along U3. U3 means that it contracts and it expands. Like a Poisson effect, this is exactly the Poisson effect. You see, it expands and contracts in space, like that. If you go higher in frequency, this is what happens. The Poisson effect becomes increasingly important. You see here it's small because it's the low frequency range. But when frequency increases, you've got this other situation. Poisson effect becomes very important. And what happens with A0 wave? A0 is bending exactly like in a beam. Then it is exactly the opposite. So you see that U3 this time is the displacement normal to the plane of the plate. So exactly as what happens in a beam, the displacement is orthogonal to the plane. So it's bending, mainly orthogonal displacement to the plane. And the U1, you see it's more or less linear when frequencies are small, okay? This is the bending in the cross-section, which is more or less linear. You go higher in frequency, things start to distort. Some other effects start to be important, and you see that there is something else happens. Something more complicated happens. Before concluding this section, I wanted to show you something here. A couple of things, a couple of details. Okay, so first detail, is there something plane strain stress state in the solution we have observed? Unfortunately, for shear waves, there is not, because this is the direction of propagation and those are the strains. So there is no. While for lump waves, this is actually a state of plane strain. Something else I wanted to tell you is how it is possible to derive the group velocity. This is actually easier than you can think, because you say, well, how can I do the derivative of omega with respect to k? It's gonna be crazy. No, because you've got the characteristic equation. And if you derive the characteristic equation once with respect to the wave number, and you put the numerator, and you divide it by the same derivative by the frequency, you invert, and this is exactly the group velocity. So deriving the group velocity is easier than what it might look like at first glance. Okay, now it's 4 o'clock. I'd like to take, let's say, a 5 minutes break, and I'll see you shortly. Okay. Okay, can you still hear me? Can you all hear me?
Yes, yes, we do.
Okay. Okay, thank you. So next part is going to be the semi-analytical finite element method, which is something which is a sort of finite element solution of the approach I presented before. So here it is explained for the case of waves in rods, but it can be basically applied to any kind of problem, also for the kind of layered plate, for instance. It just depends on the kind of solution and on the dimension of the domain you want to explore. So let's start from the beginning. Semi-analytical finite element method has this acronym, which is called SAFE, and it's a method which was developed in the early 70s to solve wave propagation problems in waveguides at high frequencies, because in those cases it is necessary to take into account the deformability of the cross-section, as we have already said. This occurs when the wavelength is the same order of magnitude or smaller than the characteristic size of the cross-section. However, the semi-analytical finite element method applies also to a wider case, a wider range of problems. This semi-analytical finite element methods consists in assuming a tentative solution which has this shape in the case of rods. You see the difference between the previous case, which was for plates. In the case for plates, I'll go back to the previous. You see that the wave modes were just a function of the height of the plate. Here, for rods, it's going to be a function of the whole area. And the propagation is enforced to occur along just x1.
Sorry, this tentative is for rods, yes? For rods?
Yes, for rods, like that. Okay? You've got a cross-section, which is the plane contained in the plane x2, x3, and an axis, which is x1. Okay? This is not easy to solve like before by hand, because here you've got to enforce three stress conditions on the whole surface. This is a mess. Then what you can do is you pick up this solution, you plug it into the bulk equations, and you obtain a list of equations, which is something like that. You pick up a solver, like for instance, a finite element solver. I did it with Console, and I will give you some suggestions also on how to implement it in Console. You pick up these equations, you write down these equations, and you enforce that you require that these equations are satisfied in the domain of which is the cross-section. You apply three stress boundary conditions on the boundary, and you solve an eigenvalue problem. Now you've got to, to note some things. First thing is this one. When you plug this solution into the bulk field equations, it happens that when you derive with respect to to x1, which is the direction of propagation, you obtain something like that. It means that the displacement field in the cross-section is unaltered, while the displacement field, the total solution, is just multiplied by ik. Second derivative, because the second derivative derives from the equilibrium, is, oh, sorry, here there is a mistake. This is a minus k squared. Sorry, if you pick up mistakes, just tell me. And then you've got these equations where you've got a not very easy situation, because you've got either k and k squared, plus omega squared. So you can decide, you can do two things. You can consider k as an eigenvalue or omega as an eigenvalue. Each of the two approaches has its own advantages and disadvantages. Initially, I preferred to calculate k as an eigenvalue. Why? Because I am sure that frequency is real. Then I decide to explore a range of frequency, I decide the range of frequency, and I iteratively solve the same problem for the range of frequency I am interested, and I recover those curves I showed you before. But here there is anyway a problem. The fact that k appears both to the first and the second power. So one thing you can do is introduce new variables, like dummy variables that are just k times the previous variable. So you add 3 more equations. Okay, so this is feasible, and the equations are shown here. So you just have these 3 additional equations that also enter here. Why it was important, this problem? Because the solution for high frequencies in rods are extremely complicated. You have to think that in a solid cylindrical rod, the solution were known analytically since 1876, but they were so complex that they could not be just visualized until mid of last century. So it's a really hard task. And then after that, the need for establishing the free boundary conditions on the external surface hindered the possibility to solve the problem for generic cross-sections. And I will show you why this can be of interest from an engineering point of view. So, as I was saying before, one approach is that you consider k as an eigenvalue and you plug in values of frequencies. Another approach, which is applied if you want to study band gaps, is exactly the opposite. In that case, for the study of band gaps, there are some theoretical results that, according to the symmetry of the material, tell you, this is not a mathematically exact result, this is a sort of, it was never proved, but it is just it's true, I guess, statistically. So statistically, the maximum and minimum amplitude of band gaps, I'll show you later what a band gap is, can be found by exploring the irreducible Brillouin zone. The irreducible Brillouin zone is a list of values of wave numbers. It's the boundary of an area. So you explore that list of values and you find maximum and minimum band gaps. But this list of values is given for k, for the wave number. Then you've got to write down the problem in the other way. Okay, yes, this is what I was saying before. Okay, I lost here a piece of what I wrote. Anyway, I'll tell you in words. when you write down these equations, either you solve in wave numbers or in frequency, you've got to be very careful. Why? Because, look at that. These are the boundary conditions. And the boundary conditions are on sigma. But in your equations of motion, since these are 3D, there are also derivatives with respect to x1. But if you enforce the solution on the two-dimensional domain, your solver will completely forget about the component along x1, but you've got to put it. Otherwise, the equations of motion are just wrong. And this contribution is highlighted here by these squares. This is the part which the software will anyway pick up. And this is the part you've got to write down. It is the blue and green part. You realize that when you write down, again, by hand or by Mathematica, or when you operate on the problem, be careful if you want to do that. Don't miss those parts. Here, if you're interested, I also have shown how to implement these equations in console when you use the coefficient form. This is an old version of console, but anyway, the most recent ones do not change much. Okay, what are the engineering applications of this SAFE? Why is that important? The different mode shapes have applications in structural health monitoring. This is the case of a rail. And this picture is taken from a paper by Nucera and Lanza di Scalea, published in the Journal of the Acoustical Society of America. This is a journal where they publish a lot of material about wave propagation. You see how different can be the wave modes. So you see this one, for instance, has large displacements in the head of the rail, while this other one are have large displacement in this part, which connects the head to the foot of the rail. So according to what you want to detect, you've got to excite a different wave mode. And we will see also in the forced excitation how you are able to excite, how you're able to choose which mode to apply. For instance, this mode with displacement in the head is the mode which is most sensitive to damage in the head. This other one, instead, is more sensitive to damage in the connection between head and foot. So it's just according to what is your need, you've got to choose the mode which is more sensitive to the aspect you want to investigate. The semi-analytical finite element method also applies to periodic media. And this is an application which we recently presented at the conference SMART, just in July 2023, together with my colleague Lepidi and Meng Wang, who is a PhD student at the moment. Probably many of you know what is a periodic material. Periodic material is realized by infinite repetitions of cells. In this case, these are square cells. In this case, but it's not necessarily true for whatever repetitions, we have a centrosymmetric material. It's got a certain symmetry. And in this case, we've used both the equation of elastodynamics, which hold in the solid phase, and also added some equations that concern the fluid phase, and adopted this solution for the strategy. We just plugged in this solution in the equations of both the solid and the fluid phase, and solved the resulting eigenvalue problem just exploiting the periodicity of the solution. We required that periodic conditions were satisfied on the boundary. And we did that. I'll explain to you after what is the advantage of doing that. And we did that by exploring the irreducible Brillouin zone, which I mentioned before, which in the case of a centrosymmetric material as this one is basically this list, this red, let's say, list. It's actually a sort of, how can I say, an abscissa, which runs through this red boundary here, where there are the arrows, that contains all the values, all the couples of wave numbers, of components of the wave number vector that one has to explore. To do what? To derive a dispersion relationship, which is exactly this one. In this case, for this periodic material, the dispersion relationship for that list of K values can be represented in this way. This is the case with voids, and this is the case with no voids. Let us observe first the case with no voids. No voids, check out these two lines. But these lines are, this is omega, this is K, C, or, well, K. They are related. These two lines are, one is the P wave and the other is the S wave. The same here in that other piece. This part, which looks like a curve, will actually look like a line if you consider, instead of the two components, the modulus. Now, let's put this part on one side and look at this other one. You see this part? This is a band gap. This is what is called band gap. You see here that all the dispersion curves cross one which is with the other. Here there is a frequency band where there are no curves. Basically, this is a frequency band where waves cannot propagate. Exactly. This is imagine a system, a non-periodic system. When it doesn't have a frequency, a natural frequency at a certain frequency, just cannot resonate. You cannot freely, you can force the system, but the system cannot exhibit that frequency for free vibrations. This is exactly the same story. Why is this approach different from application of the Floquet principle. And what is the Floquet principle? You might have heard of it when you've probably heard about periodic structures. Remember that here, the only thing I did is just picking up the tentative solution, substituting in the field equations, and applied periodicity conditions. Here, totally different story. Let us consider a one-dimensional system to keep it simple. Let us consider a system like that, which according to the axis, just one-dimensional system, one-dimensional axis, it's got, let's pick up a taut string, as we did before, same equation, but the only difference with respect to what we did this morning is that this time the density is no longer constant. It is a periodic function. It's a function like that. It's got a spatial variation of mass density per unit length, which repeats after a given modulus, which here I've called D. Sorry for the inconsistencies. I will have to reread it. Maybe in 20 years, this will be perfect. What do we do? Same story. We define a solution and plug it in the equations of motion. But we did do something different from what we were doing before. Before, we assumed a given amplitude. Right now, here, we no longer have a constant. We have a function, a function of space. This is called a solution, which is spatially modulated. Pick it up and substitute in the equation of motion. Now, if you give a better look at that and consider the same equation but written in terms of the shifted coordinate, you can see that x is just equal to x prime plus d. So I can just pick up the previous equation and I plug it in x prime plus d instead of x, which is equal, as you see from this structure. And then observe that all this has to be equal to 0. This term is just a multiplicative constant, so you can take it off. Moreover, since the distribution of density is periodic, you can see that this delta rho of x prime plus d, which is delta rho of x, is nothing but delta rho of x prime, thanks to the periodicity. Then, apart from the renaming of the x-coordinate, the only change resulting from shifting the coordinate is f of x into f of x prime plus d. But since the periodic structure is the same in the two coordinates, the solution must be the same in the new coordinate as in the old. This is just the Floquet principle, and that's it. The modulated part has to be also periodic. Then what is the idea? Since the modulated part of the solution is a periodic function, we can think of expanding it in Fourier series, like that. You expand f of x, modulated amplitude, substitute it in the solution, and basically the problem reduces quote, between quote, because it's not easy to solve, but anyway, it reduces to finding the coordinates of this series, sorry, the coefficients of this series. So A sub n. And this can be found on substituting the series expansion in the tentative solution in the equation of motion and projecting onto the harmonic basis. You integrate over the size of the cell, and considering the fact that there is this orthogonality relationship, you obtain an infinite set of algebraic equations that are something like that. And in the end, you obtain this system of equations, which is a homogeneous algebraic system that, again, gives rise to a characteristic equation which defines the dispersion relationship between omega and the Floquet wave number. The problem is that this is a series, again, and this is an infinite series. So numerical solutions, an infinite matrix, you saw before that we dealt with an infinite matrix, and we solved the problem using the translation symmetry. So numerical solutions can be obtained by truncating the infinite equation to a finite number of equations and increasing the truncation limit until the solution converges to a desired level of accuracy. And, moved back to the next session. And so you see what is the difference between applying the Floquet principle and applying just safe and periodicity conditions. To me, it seems easier the first approach. But I have not implemented the Floquet principle, so I'm not sure. An idea, if you cannot sleep at night, you want something to, like crosswords to do, could be to see if this problem can possibly be solved using the translation matrix. That might be possible. I don't know. Okay, so last subject. I'm a little bit tired, but I think we can do it because it's not really very long, and also because it gives you a nice conclusion to this part. Last subject concerns the forced response of plates using the wave mode expansion. Because up to now we have considered free wave response. But if we want, how can we actually see and observe those wave modes we've been talking about? We can find ways to excite a specific wave mode. And this is feasible, and you will see at the end of the lesson how this is possible by loading a plate with a source. In this case, I will consider a finite-sized source. And this is exactly what happens when a disturbance is applied with a piezoelectric emitter. So the problem we've got to solve is exactly this one. Let us consider the case of a plate, but it holds for whatever waveguide. We've got a waveguide, and this drawing here is an external load. So the approach which is used in waveguides is pretty similar to what is done, pretty similar but with some differences. It is pretty similar to what is done in beams, plates, or every object that have a boundary and where you can use, where you can exploit the orthogonality of the eigenfunctions. Because in practice, when you solve a forced vibration problem, forced vibration, remember that in the literature, there is this big difference between waves and vibrations. What is the difference? Vibrations are solutions that concern structures that have boundaries and where you can express the solution in terms of eigenfunctions superposition, which is in terms of vibration modes. Waves, instead, are transient problems where the solution can be expressed in terms of wave mode superposition. Now, the case is slightly different because wave modes are orthogonal. And moreover, the normal modes are orthogonal and complete, which means that whatever function can be exactly represented in terms of a finite or infinite number of functions that belong to the set of wave modes. How is it feasible? You know that wave modes, which I wrote here like phi over sub m, are this function. They satisfy these orthogonality conditions. You can express a solution as a superposition of modes because you are able to derive the coefficients of the series. But this is not pretty much the same with wave modes, with wave modes. Because the wave modes do not directly satisfy an orthogonality conditions. They instead satisfy this other relationship, which is called reciprocity condition, and which derives from the relationship between two solutions, which are called here V1 and V2 in terms of velocity or displacement. This is the same. Two solutions that exist at the same frequency. This is a mess. I tell you, it's not easy. But anyway, so 1 and 2 are these ones. Same frequency, different wave numbers. There are two different solutions, two different wave modes. And they are not, unfortunately, orthogonal in the classical way. They are orthogonal in this other wave. In fact, they are not called orthogonal, they are called reciprocal. This makes things much more complicated, and the, let's say, reciprocity condition for a plate can be expressed in this way. So it is the integral over the cross-section of the sum of these products, and here you've got the wave numbers. Okay, I don't want to go too much into the details, because as you see, they are crazy. And I will honestly thank you for double checking if you feel like, if you can't sleep at night. And because I haven't found the details of this solution anywhere. I mean, I just found the result. And I mean, the results are okay, but I'd like to understand more of the single steps. But what I know for sure is this. And this is related to the excitation of a plate. This is the result, which in practice is these lines, oops, sorry, these lines are the dispersion relationship of a plate. How are these obtained? These are obtained from a numerical experiment where I picked up a layer, I excited with a broadband pulse, meaning that I explored all this range of frequency by a broadband pulse. What is a broadband pulse? For instance, in time is a, sorry?
Square wave.
No, I prefer using a Gaussian wave, like a Gaussian wave. If I want it really broad in frequency, I do it very narrow in time. And so I launch in a plate this disturbance. I record on the surface the response, the time histories of the response, and then I got here the list of solutions in time and space. Then I do a two-dimensional Fourier transform, and I get that. You see that this one is pretty similar to this one. They are the same. Now they are actually, oh no, they are like that. Yeah, yes. Because frequency. Yes, the same curve. So what is the idea? The idea is that if you want to excite a specific mode, you've got to go with a forcing function which has exactly the frequency of that mode and try to excite in space the displacement field of that specific wave mode. Then you let it go, forget about the initial disturbance. I mean, forget about. There is a way to avoid that you see too much of a transient. and it consists in applying a force which starts slowly in time. You've got to avoid abrupt changes. For instance, the case of a square wave. That's not really good, because if you don't put some damping, you are going to see a transient solution which will confuse everything. Otherwise, you've got to put damping. But why? Why doing so? You can use a very nice Gaussian function. Okay, and this is the conclusion for today. And you are free to ask questions. If I cannot answer, I will think about it and answer in the future. I hope this Friday or even later. Okay. Questions? Suggestions?
I just wanted to ask if this material which you had presented is somewhere put on the website, or
yes, I will make it available after the end of the classes. I will send you the PDF, and also consider that I've got a website, the website which is provided from Sapienza, from the university, where I am used to upload the recordings of these classes. I didn't do it last year, but I did that a couple of years ago, and I also upload the PDF of the presentation. So you will have them mailed to you if you registered for the course, or either you will be able to download them from my website shortly.
yes. And about this, I just wanted to ask if the form with the deadline for 4th of September was the same as the form from July or not, because I did not.
Okay, but look,
Right.
in any case, if you don't get it, you just write an email to me, and I will mail them to you.
Okay, thank you, thank you.
Yes.
The work regarding structures. You didn't consider any fluid structure interaction?
No. No, wait, periodic structure, yes. In that case, there is, but two things. Okay. Fluid and structure here, they interact just by pressure. I mean, pressure on that surface has to be the same. And in that case, there isn't transport of fluid between the cells. No transport of fluids. And also there is this is an irrotational fluid. We put some symmetry conditions on this gradient of the displacement field, also for the fluid. For sure, one could consider more realistic situation, but if air is still, I guess this can be, I mean, at least as a first approximation, can be useful to understand the behavior, at least more or less, even because the majority of studies just do not involve fluid. We did that because we were interested in understanding whether we were able to find cases where there is both fluid and solid band gaps. so that a material which is both which can both protect from vibrations and sound can be implemented. Okay, guys, if there are not any questions, I'll exit the meeting, and I'll see you tomorrow. Tomorrow at 3 p.m. there is gonna be the lesson by Professor Trovalucci. Okay.
Thank you.
I'll see you tomorrow. Bye bye.